Today we're going to look at what does it really mean to be a zero? Why do we talk about zero so much and solutions and factoring and all that stuff? I mean, what does it really mean? What's the point? You know, no matter what type of equation you're solving, whether it's linear or quadratic or to the fourth, fifth, sixth power, what we usually try to find are two things: the maximums and minimums, the turning points. That's usually where you have a maximum or minimum, and the zeros. And those are the important things when you talk about real life. You're looking at, the maximum sales, the maximum area of something. When you throw something into the air, when does it hit the ground? That'd be a zero. Real life stuff is modeled by functions, and we can plug data into some kind of program, and it's going to kick out a function. It's going to predict things for us and tell us what's going to come in the future based on what's happened in the past. And that's basically what polynomials are. And a quadratic is a polynomial. It's just a more specific polynomial with a power of 2, so we call it a quadratic. So this all started, when you think about it, it all started with linear equations. If we have, a linear equation, it's just a line, and we graph it, we look at the zeros. When does it cross the axis? Whether it is the x-axis right here, or whether it's the y-axis down here. And in real life, those two things would make sense. You're talking about if you walk somewhere at a constant pace, that is a line, that is a linear equation. You would only look at the positive version of this line because you can't, have negative distance, so you would just look at the positive version. Anytime you have a constant change, the change is the same from instance to instance, that is a linear equation. Those are usually, pretty self-explanatory. You look at something where you got sales, right? Sales can be part of a linear equation. Something going to cost $30 or $10 to make, and then it costs as a base, $10 as a base, and then for every single one you make, it costs you 30 cents. So you'd say, 0.30x. And that's how much it costs you to make X number of whatever things. And that would be a linear equation. The base cost of materials, or maybe the 10 might be the base cost of a factory. And then the 30 cents might be how much it costs you in materials to make each time. So that is a linear equation. And, those happen quite often. The next thing we looked at was quadratics. And when you look at a quadratic equation, let's just do one of... let's do one look like this. All right, so there's our quadratic equation. Obviously not drawn perfectly, but you get the point. We have a couple things going on here. We've got a vertex right up here. That would be our maximum in this case. We've got a couple intercepts, right? A couple x-intercepts. So we got a maximum, a vertex, and we got some x-intercepts. This could be a possible equation for throwing something in the air, projectile motion. Anytime you throw something in the air, it has to go up and come back down at the same rate. So I forgot the y-intercept. Depending on where we throw this ball from, or this whatever it is, this object from, is going to depend on where the y-intercept is. So we're standing, say that's 10 feet. We're standing 10 feet above the ground, and we throw it. It reaches a maximum, and then it comes back down and hits the ground. This might be a height versus time graph. So when you write a function of this, you might write something like, h of t, height as a function of time, is equal to maybe something like negative t squared, plus 2t plus 10. I don't know, I'm just making this stuff up, but negative t squared has got to be negative because the parabola is facing down. 2t, and then 10 is our height. That's where we started from. So 10 feet is the elevation that we threw it from, then we threw it up and it came back down. And at any time, we could figure out the height of this ball or this object that we threw. That is a quadratic. And those are pretty self-explanatory because you can actually go out and throw something into the air and it look like a quadratic, so you can see that. What's going to start to get a little more complicated is when we start talking about polynomials of higher degrees. And you might have, let's just start off real easy with an x to the third. This is what an x to the third function looks like. Anything x to the third, a positive x to the third, it's going to, kind of take this shape. This is the shape that an x to the third function takes. It's really hard to imagine something following this path in real life. Projectile motion, a quadratic, it's really easy to see, but this right here, doesn't make that much sense. But if I were to use, some real data and actually plug in real data, and you talk about rising and falling of, the economy, you talk about all those different kinds of things, the x-axis could mean a multitude of different things. It could be, this could be like the average price of something. This could be the average temperature, and the x-axis could be 0. And you can use a quadratic function to model, what the temperature is going to be in 100 years based on what the temperature was 100 years ago. And then you can use a polynomial to model that. And a lot of times, we might have a few data points on a graph. For instance, if I was to just draw a graph and then plot some points, let's go with something, like this. Let's say we got, points like this. We have calculators and computer programs that are going to choose what we call a line of regression. And what that means is that it's going to basically pick an equation of a line that goes through or averages through, the maximum amount of points here. And if you look, if I was just to draw a straight line like that, that doesn't go through very many points. It doesn't get around very many points. If I was to draw, a quadratic, I might be able to hit some of them like this. That might be close. But what your calculator is going to pick the best one. And this is actually, if you look, it follows a path. Right? So this type of graph, this cubic, actually gets the closest to these points. And it makes sense that if I were to pick, another point, it would come up here. So it's going to predict that the more points come up here. And that's the reason we're going to use polynomial functions. Now, the zeros, are going to come in handy. They would be like, right here. The maximums and minimums, will come in handy. And it's actually easy to figure out how many zeros you're going to have and how many, maximums and minimums possible you can have. And that's with the fundamental theorem of algebra. And we're going to get into talking about that next time. But this is just kind of an overview of, zeros and minimums and maximums and why they're important and why they talk about them. So for the future, you can always think about, why do we solve for 0? Well, it's important where y equals 0, that x-intercept. And if you think about it, if anytime we have an equation, say we have something like y equals 2x plus 4, or y equals, x squared minus 2. You want to look at when these values, when y is 0, because that's gonna be your 0 of the equation. That's what's going to cross the x-axis, because at the x-axis, that actually is the line y equals 0. So every time you cross that line, your y equals 0. That's why we sub in 0 for y, because we want to look at when this graph crosses the x-axis, and at that exact instance of the x-axis, y is 0. So we plug in 0 for y and solve. That's why we always say sub in 0 for y and solve, because that is where it crosses the x-axis. And then we'd go on and solve. We'd figure out our answers. We'd figure out our values of x that make this equation true. And to do that, we would add 2 to both sides over here, subtract 4 from both sides over here, and solve and figure out what value that is. That's solving for x when y equals 0. That is finding the solutions of the equation, finding the roots of the equation, finding the zeros, finding the x-intercepts. Those are all the same thing. So whenever it asks you to do that, they're all the same thing, and you don't have to worry about that. So just know that if it's asking you for zeros, x-intercepts, solutions, roots, you're basically doing the same process every single time. And graphically, you're looking for when that graph crosses the x-axis. That is when y equals 0. That is your solution to your equation when y equals 0. We've already learned multiple different ways on how to solve these when y equals 0, whether it's with a linear equation or whether it's with a quadratic equation. And we're going to apply those same kind of concepts to more difficult problems, polynomials, when we have higher and higher powers. So your linear equations where you had like, 2-step equations, or, even multi-step equations. And then you had quadratics where you had, factoring, factoring to solve. And then you had, completing the square, everybody's favorite. And then we had the old reliable, the one that works every single time, and that is the quadratic formula. And the quadratic formula does work every time because the quadratic formula is derived from the standard form of a parabola. So it only makes sense that it's going to work every time because you are finding the x value in that standard form. So the quadratic formula always works. And then there's if you have access to it, you can always graph it. And that's with quadratics. That's with anything. Quadratics, any power, linear equations, whatever. You can always graph it and see where it crosses the x-axis. So these are 5 different ways that we've talked about, and two-step equations only. That's just the basic, like this problem up here. Subtract 4 from both sides, and then you get negative 4 equals 2x plus 4. 2x, it's about itself, and divide by 2. That'd be your 2 steps. So you get x equals negative 2. That'd be your 2 steps. Two-step equation, that kind of thing. That's usually only going to be with linear equations. That's when we talk about two-step, 3-step, multi-step equations. Dividing, multiplying both sides by something, so on and so forth. Factoring, completing the square, quadratic formula. Those are obviously going to be for, especially completing the square and quadratic formula. Those are for your quadratics. Those are for x squared. Completing the square, x squared, quadratic. It's a quadratic equation, quadratic formula. But factoring, it can be for anything. You can factor. I could have factored this linear equation up here. I could have pulled out a 2 and done 2 times x plus 2. I could have factored that. You can factor polynomials of a higher degree if they have a common factor. And there's actually another way to factor them if it works, and that's factoring by grouping. It's a very specific case, but it does work sometimes. So factoring is going to carry over through all of our different types of polynomials. So I'm not going to go into how to actually solve equations with these methods because we've talked about them before, but I just kind of wanted this to be an overview of, what zeros were, why they were important, and how we, what does it really mean? How can we use them in real life, and why do we use them in real life, and so on and so forth. So if you have any questions, feel free to comment, let me know. I'll try to reply back to them as soon as possible. Thanks.